It is a great honor to present the next invited speaker, Professor Fernando Coda Marques from IMPA in Rio de Janeiro, Brazil. Professor Marques was born in San Carlos, São Paulo, which might come as a surprise to some, but he grew up in Maceió, in Brazil, beautiful region northeast. He received his BS in Alagoas in 1999. He also received a master's at IMPA in 1999, and he received his PhD in 2003 at Cornell University under the scientific guidance of Professor José Fernando Escobar. Professor Marques is one of the most prominent geometers of his generation and a South American superstar. His mathematical results are beautiful, striking a balance between highly technical and extremely deep. Perhaps his best-known achievements include his joint works on compactness and non-compactness of the space of solutions of the Yamabe equation, which is also known as change conjecture, the path connectedness of the space of metrics of positive scalar curvature, constructing counterexamples of the Lunar Conjecture, and most recently his proof of the Willmore conjecture, a long-standing problem in differential geometry. Professor Marques has received several accolades for his amazing work. These include the Third World Academy of Sciences Prize in Mathematics in 2012, the Ramanujan Prize in 2012, and the Umalka Prize also in 2012, among many others. On a personal note, I can add that Professor Marques is a great soccer player, a swift forró dancer, and a football prodigy. Without further ado, let's hear him talk about the minimal surfaces, the Willmore conjecture, and the energy of limits.
Today we're going to talk about some joint work with Professor Andre Neves from Imperial College in the UK. And the goal is to present to you the solution that we found for the so-called Willmore conjecture, which is a conjecture in classical differential geometry, and some other applications that we found later on of the minimax theory of minimal surfaces that I will mention throughout the lecture. So the Willmore conjecture is a classical question because it's a question about surfaces in 3 space, differential geometry of surfaces in 3 space. And it has a simple statement, and it's very easy to motivate. So if you want to know what the Willmore conjecture is about, so the question is, what is the best torus in R3? So for the layman, one could ask, what is the best donut, if one wants. Of course, we have to make it precise, but that's what the Willmore conjecture is all about. And we found a solution sort of using the theory, finding this connection with the theory of minimal surfaces. Okay, so let's get started. Let's see here. So we start from an abstract closed surface with some genus G. We fix one topological type. So for example, if the genus is 0, then the surface is a sphere. If the genus is 1, then we're talking about a torus, and so on. So one fixes one of these topological types. And then we ask the question, what is the best realization of such a surface into Euclidean 3 space? So what is the best immersion? So for each such fixed topological type, there are of course infinitely many shapes the surface can assume in Euclidean 3 space with curvatures. And somehow you want to find among all such possible shapes, you want to say what is the best one, the most elegant one, if you want. So if the genus is 0, then it's natural to think that the solution should be a round sphere. Of course, a round sphere is the most symmetric shape a sphere can assume in Euclidean 3 space. So whatever precise sense you make out of this question, the answer for genus 0 should be a round sphere. But if you ask the question, what is the best torus, then the answer is not so clear. You have to make it a little bit more precise. And we're going to do that through differential geometry. So the idea is that we're going to look at the curvatures of the surface. So recall that the geometry of a surface in free space is described by these two numbers called the principal curvatures. So what you do is that you pick a point on the surface, you take a perpendicular direction passing through that point. So for every plane passing through the point and containing the perpendicular direction, you look at this intersection with the surface. So the intersection is, of course, a planar curve. It comes with a curvature. So as you vary your plane around the axis, you see these different curvatures. So the principal curvatures are just the maximum curvature and the minimum curvature that you see. They always come in orthogonal directions. Those are very important numbers in differential geometry. So out of these two numbers, one can define the classical notions of curvature in differential geometry. Namely, one can take the average of those two numbers, the principal curvatures, and that's called the mean curvature. And one can also take the product, that's called the Gauss curvature. So the idea is that in order to find the best torus, say, we would like to find some interesting energy and set up a variational problem. So we want to find some interesting energy and ask what is the minimizer for that topological type. So it's natural to try to find energies which are scale invariant, because you're only interested in the general shape of the surface. So if you want a scale invariant functional, of course area does not work. So if you want a scale invariant functional, because the surface is two-dimensional, it's natural to integrate over your surface an expression that is quadratic on the principal curvatures. Okay? For example, one can integrate the Gauss curvature, which is, of course, quadratic, but if one does that, then the answer by the famous Gauss-Bonnet theorem is, well, this is always equal to 2 pi times the other characteristic. So this is a topological number. It does not distinguish between different shapes. So we don't want to do that. But fortunately, there is something else that one can do. One can integrate the square of the mean curvature. So that's the simplest curvature functional that's scale invariant. And that's the function that we'd like to consider. So that's called the Willmore energy of a surface inside free space. So this number, this energy, is invariant under rotations, translations, and also scalings, but it's actually also invariant under inversions. So it's invariant under the full group of conformal transformations, and this was known since the 1920s. This was known by people like Blaschke and Thomson, who were working in conformal geometry. So that's a conformal invariant quantity. That's a very remarkable property of this function. Let me also say that this is sometimes called the bending energy because it's related to elasticity, and it appears naturally in some physical situations. So for instance, it had been proposed by Sophie Germain and Poisson in the early 1800s to describe elastic shells. So there's an interesting story behind this. So at the time, the Paris Academy of Sciences established a contest. So the challenge was to derive some mathematical theory that would explain some experiments with vibrating metal plates that were available at the time. And after hard work, Sophie Germain managed to win the contest through her paper on elasticity. It also appears in mathematical biology in the so-called Helfrich model. This appears as related to the energy. Okay, so the subject was reinitiated by Willmore in the 1960s, who proved the following results. So he proved that the Willmore energy of any closed surface in R3, no matter its genus, is always greater than or equal to 4 pi. And that number is achieved precisely by the round spheres. So if you ask what is the minimizer for the Willmore energy among all closed surfaces, the answer is a round sphere, which is compatible with this intuition that the round sphere should be the best surface, right? Most symmetric one. So he did that with no assumption on the genus, and then he asked the question, that became known as the Willmore Conjecture. It was proposed in 1965. So he asked the question, what is the minimizer for genus 1, for torus? So the conjecture was that the integral of the square of the mean curvature of a torus, in other words, the Willmore energy of a torus immersed in R3 should be at least 2 pi squared. So that was his prediction. And in order to come to this number, what he did was the following. So he considered a circular tori of revolution, which is a very simple class of tori in R3. So you pick a circle in the plane, let's say xy here in the picture, and then you rotate the circle around the y-axis. This generates a torus of revolution with circular section. And among such a class, he proved that the best one was the one such that the ratio between the distance from the center of the circle to the axis with respect to the radius of the circle is square root of 2. So this is a picture of these torus, and this guy has Willmore energy equal to 2 pi squared. So this is the best. I mean, his prediction was that this is the best guy, but of course the problem is conformal invariant. So if you pick your favorite conformal transformation and you apply it to this torus, then again you see you have a torus with energy 2 pi squared also. So I cannot resist to show you a little gift that I got from 2 PhD students of mine. So they were in the summer school in Park City a couple of weeks ago. So apparently there was a 3D printer there. So they managed to produce this torus. So what they did was they took the guy, the guy of revolution, and then they applied this conformal transformation. They put the equations in Mathematica, and that's the guy, right? So it's kind of cooler than the one in the picture. So it's kind of nice. So I showed this at IMPA last week, and some people, more than one person, came to me and said that they didn't even know that this technology existed. So it's kind of amazing. Anyway, so you can apply conformal transformations, and you see different tori with energy 2 pi squared, of course. So you can ask the question, why 2 pi squared? So in order to answer this question, we have to look at the stereographic projection, which is a conformal transformation from the 3-sphere minus the point onto the Euclidean 3 space. So since the problem is conformally invariant, we can try to formulate it in terms of surfaces in the 3-sphere. So if you pick a surface sigma contained in the 3-sphere, and if you can take its projection, it's a stereographic projection onto R3, then if you compute the Willmore energy of this projection, you can do a calculation. This turns out to be the integral of the surface in S3 of 1 plus the mean curvature squared. So the formula changes a little bit because this is one guy over here, but anyway, this is complete. Those are completely equivalent problems because you can go from S3 to R3 and the other way around too. So this is the point of view that we will adopt in this talk. So we'll consider surfaces in S3 instead. So for a surface sigma in S3, the definition should be, the Willmore energy of sigma should be the integral of 1 plus mean curvature squared. So now the mean curvature is computed with respect to the spherical geometry. So one can easily see that because this term is non-negative, the Willmore energy of sigma always dominates its area. And that's a simple observation, but it's kind of important because later we'll see that one key ingredient in the solution of the conjecture is the fact that this Willmore energy, it not only dominates the area of the surface itself, but actually dominates the area of a whole 5-dimensional family of surfaces that we are going to construct later on. If the surface happens to be minimal, so remember the minimal surfaces are those surfaces which are critical for the area functional. So the first derivative of the area functional is 0 with respect to any variation. And we know lots of minimal surfaces, closed minimal surfaces in S3. So if sigma is one of those, then this term of course drops out, and then one sees that its Willmore energy is just the area. So there was already some connection with the theory of minimal surfaces. What we did was to make this connection much more precise through this MEMAX theory that I'll mention later on. So let me say that the simplest minimal surface in the 3-sphere is the equator, a great sphere, with area 4 pi. So it's, again, it's compatible with the fact that the Willmore energy of a round sphere is 4 pi. But the next one, the next simplest minimal surface after the equators is the Clifford torus, which is defined as a product of circles. So you choose the radii to be equal, and so that this guy lies in the unit 3-sphere. It's very easy to check that this is a minimal surface. It's also very easy to compute its area because this is just a product of circles. So if you do that, you get that the area of the Clifford torus is 2 pi squared. And this is no coincidence because if you choose the stereographic projection right, the projection of the Clifford torus is going to be the guy, the circular guy of revolution, right? So the answer to the question why 2 pi is this a natural number is, well, 2 is the area of the Clifford torus. Okay, so it has a long history, so let me the partial result. In the early 70s, Willmore and independently Shiohama and Takagi, they proved the conjecture for surfaces that are tubes. So you look at you take a space curve in R3, you look at a tubular neighborhood of constant radius, and the boundary of that tubular neighborhood is a tube. So they verified the conjecture for this particular class. 76, Langevin and Rosenberg proved that the Willmore energy of any knotted torus, in other words, a torus that cannot be brought to the standard position through an isotropy of the ambient space. So they proved that if the torus is knotted, for example, this torus in the picture, I think it's knotted, the Willmore energy should be bigger than 8 pi, bigger than or equal to 8 pi, which is better than 2 pi squared. So this verifies the conjecture for that class also. In 1982, Peter Lee and Xingtun Yao, in a very important paper, they proved a couple of results. So they introduced this notion of conformal volume. And among those results, they proved that if the surface is not embedded, in other words, if it has at least one self-intersection, then its Willmore energy should be bounded below by 8 pi. The idea is that this is a kind of generalization of Willmore's previous result, because they prove that if you have a triple intersection, then the energy should be bounded by 12 pi and so on. So they're kind of part of the same family of results. So since this is better than 2 pi squared, this is bigger than 2 pi squared, in order to prove the conjecture, we might as well assume that the surface is embedded, and that's what we do in the paper. They also proved the conjecture under conditions on the conformal class of the surface. That's what they did in this important paper. In 83, Chen proved the conjecture for the class of flat tori in the 3-sphere. So here's a picture. Langer and Sigan in 84, they proved that the conjecture is true for tori of revolution, where now the section doesn't have to be circular anymore. And in 86, Montiel and Ross, they improved the previous result of Li Yao, so they enlarged the set of conformal classes for which the conjecture is true. In 91, so we heard about this paper after we posted ours. Apparently, the conjecture had been verified in the laboratory by some Benson and Moots. So they wrote to us by telling us that they had proved the conjecture many years ago. It's kind of interesting. So some other important results. In 93, Leon Simon proved that there exists a torus. There exists a minimizing torus for the Willmore energy. And let me mention also that in the late 90s, so independently, Antonio Ross and Peter Topping, they proved the conjecture for tori in S3, which are invariant under the antipodal mapping. So those two proofs are different. Somehow our proof was initially inspired by the paper of Antonio Ross. But one can also study critical points. It's not, there are many saddle type critical points for the Willmore energy, so one can study those, and many people actually do write beautiful works on those guys. For example, Robert Bryant, he was able to classify all the critical points for the Willmore energy, which are topological spheres. So here are some pictures. Pinko found many of those which are actually topologically tori. So here's some pictures. Of course, they are all unstable, so they are not minimizers, but there are infinitely many of those. So there's a lot of activity in the field. Okay, so let me now come to the statements. So the main theorem of the paper. So the paper, it's already accepted. So you can, if you want, you can access it through the journal's website. So the main theorem of the paper is theorem A, which says the following. So if you have suppose you have a closed surface in S3, which is assumed to be embedded. We can do that because of Li Yao's result. And suppose that its genus G is greater than or equal to 1. Then its Willmore energy is greater than or equal to 2 pi squared. And we can actually characterize the case of equality. We can only have equality here if the surface sigma is a conformal image of the Clifford torus. Right? So of course theorem A implies that the Willmore conjecture is true. But it proves more because we managed to prove the 2 pi squared bound also for higher genus surfaces, which was not previously known. So because of rigidity, actually, so we also know that for higher genus, the minimizer, these guys also exist. So it should be strictly bigger than 2 pi squared. Okay, so this proves the Willmore conjecture. But actually, since we want to use the theory of minimal surfaces, we have to prove a statement about those surfaces first. So theorem B looks like a corollary of theorem A, but it's important to prove theorem B first because this is a statement about minimal surfaces. So again, under the assumption that your surface is closed, embedded, genus greater than or equal to 1, but now let's suppose it's minimal, then its area, which in the case of minimal surfaces is just equal to the Willmore energy, is greater than or equal to 2 pi squared, and the equality holds if and only if sigma is the Clifford torus, maybe up to a ambient isometry. So this is saying that if you want to look at the area of minimal surfaces in S3, I said that the lowest area, the one with lowest area is the equator with area 4 pi. So this theorem is saying that the next one in the list is the Clifford torus with area 2 pi squared. Okay, I said that we're going to prove it using the Mimex theory of minimal surfaces. So let me illustrate the Mimex method with a simple example. So suppose that you have a piece of a surface shaped like that, and then you want to look at the height function, and you want to find the critical points of the height function. So it's very easy to find, the C here, which is the minimum point of the height function, but it's more involved, slightly more complicated to find unstable guy, the C1 with, which in this case is equal to 1. Right? So remember that the index is just the number of negative eigenvalues of the second derivative. So in order to find this guy of C1 with index 1, what we can do is the following. We can consider all loops which go into the hole. So those are, say, these black loops here in the picture. So we have this homotopy class of loops. And then for each such loop, we can take the sup of the height function over the loop, and then we try to minimize this over the class of all loops. So by doing so, we eventually arrive at the critical point C1. Right? That's the Mimex process. So the height function at C1 can be achieved by doing this Minimax procedure. So an important observation here is that this guy has index 1, and we were able to find it by doing Minimax over one parameter families, right? Curves. This is just one parameter family. So in general, Morse theory tells us that if you want to detect an index k critical point, one has to do Minimax over families with k parameters. Right? So it's harder to construct higher index critical points. And that's an important observation here because the key point in the solution is that we will construct the Clifford torus by doing Minimax. But the Clifford torus turns out to have index 5, so I'm going to mention it later. Okay, this is just a simple illustration of the Minimax method. So minimal surfaces are critical points for the area functional. So here in this picture, you can think that this represents the space of all surfaces, and you replace the height function by the area functional, and then you can try to do Minimax to find critical points. those surfaces are precisely these surfaces with zero mean curvature, minimal surfaces. The equator, so minimal surfaces, they are critical points, and they also come with an index. So the Morse index of the equator, or great sphere if you want, happens to be 1. There is one direction to decrease area, push up, for example. And in fact, you can produce the equator by doing minimax. So the idea is that you take the 3 sphere with radius 1, for example, then you consider non-trivial sweep-outs of S3 by surfaces. So you consider 1-parameter families of surfaces which sweep out the whole 3 sphere. So these surfaces here are represented by these red curves. So for each such sweep-out, you look at the soup of the areas, and then you try to minimize this over the class of all sweep-outs. And if you do that, the number that you find is going to be 4 pi, and the critical point is going to be the great sphere. Again, note that the equator has index 1, and then we are able to find it through minimax over 1-parameter families of surfaces. In fact, you can do this procedure in any compact Riemannian 3 manifold. So if you want to find a minimal surface in some Riemannian manifold, what you can do is, again, you can consider non-trivial sweep-outs, take the soup of the area, minimize that, and by doing so, we prove that there's always a minimal surface, which is embedded in the closed. So let me mention the main ingredients in the proof. So the first is, let me just say that the key question that we asked ourselves, that somehow we discovered that was, connected with the Willmore conjecture was, okay, we can produce the equator by doing minimax, but what about the Clifford torus? So the Clifford torus is index 5. So can we produce the Clifford torus as a min-max minimal surface? And here's the first evidence that such a thing is possible, because for each closed surface in S3, one can actually construct, in a canonical way, a 5-dimensional family of surfaces, which I denote by sigma Vt. So V is a parameter in the unit ball, and T goes from minus pi to pi. So this 5-dimensional family of surfaces contains the original guy, and it has the property that the area of each guy in the family is bounded above by the Willmore energy of sigma, right? So the idea here is that you have your original surface sigma. First you apply a conformal transformation, and then that corresponds to the V parameter, and then you look at equidistant surfaces, and this corresponds to the T parameter. So the inequality here actually follows from the calculation of Antonio Ross, who had considered this equidistant deformation. The second ingredient is that the Clifford torus can be characterized by its Morse index. So if you have a minimal surface in S3, no assumption on the genus, and suppose that its index is bounded above by 5, then Urbano in 1990 proved that this surface has to be either the Clifford torus with index 5 or the great sphere with index 1. There are only these two possibilities. So there's a characterization of the Clifford torus by its index, if you want. That's a very important theorem that we use. And finally, we need some min-max theory of minimal surfaces that applies to our setting. Actually, such a theory exists. It was developed first in the 60s by Almgren and finished in 1981 by his PhD student Pitts. It uses a lot of geometric measure theory, but the point is that such a theory exists, a theory that deals with multi-parameter families. So at this point, let me maybe just mention what was the program that we had in mind at the time, so in order to prove the conjecture. So the idea was more or less the following. So we have the surface in S3, let's say a torus if you want, for which we want to prove the Willmore conjecture. So we know that there's this 5-dimensional family of surfaces passing through that guy with the area bound. Then we thought, okay, maybe we can consider minimax over all families which are homotopic to the canonical one. So if one does minimax, maybe we'll be able to produce a minimal surface in the end. The area of this minimal surface is going to be bounded by the Willmore energy of sigma. So because the family was 5-dimensional, we thought, inspired by Mo's theory, that maybe we are able to prove that the index of this minimal surface is bounded above by 5. And then Urbano's result tells us that this minimal surface has to be either the Clifford torus or the great sphere. And then we thought, okay, maybe if we find some new topological ingredient, some new topological idea, we'll be able to rule out the possibility of producing great spheres in the end. So if you do that, then we have managed to prove that the minimal surface is the Clifford torus that has area 2 pi square, and there you go, the Willmore energy of sigma must be bounded below by 2 pi square. So that was the idea. Of course, the crucial thing here is how does one rule out great spheres? Okay, maybe let me just formalize a little bit more the Mimax theory. So we consider families that are defined in the n-dimensional unit cube, and that take values in the space of closed surfaces in M. In order to be precise, for those who know some geometric measure theory, this is actually the space of integral currents, integral two-dimensional currents with boundary 0. Well, one can just think of those as closed surfaces in M. So then once we have a map, we can look at the homotope class of such a map relative to the boundary, so with fixed boundary values. And for each family in this homotope class, we can take the sup of the areas. That's called L of phi prime. And then we minimize this over the whole class. And then we get this number, that's the Mimax number, which we call the width of pi. And the Mimax theorem tells us that if this number is bigger than the areas on the boundary, which is a very natural condition if you think of the mountain pass lemma, then this number is actually achieved by some minimal surface. There exists a smooth embedded minimal surface which could be disconnected, maybe with integer multiplicities. So the area here has to be counted with multiplicities. But the point is that such a guy exists and it achieves the Mimax number. Okay, so that's the theorem that we would like to use. A remark here is that, so if by some chance you have some optimal family in the homotope class, so an optimal family is a family for which the sup of the areas is already the Mimax number. So you might imagine in the previous example a curve such that its sup of the height function is already the critical value. So such a curve must cross the critical point. So something similar happens here. If you have an optimal family, then it must cross a critical point. So in other words, the surface can be the family must contain a minimal surface like that. Okay, so this is just a remark because I want to illustrate later the idea of a theorem. So that's the Mimax theory. Finding minimal surfaces, how does one find minimal surfaces in Riemannian manifolds? I already talked about that. So one way is you pick, for example, a Morse function defined on a manifold. Let's say the image is the interval 0, 1. Then you can look at the level sets of this Morse function. That's a non-trivial sweep out of your manifold. Then you can consider the homotope class of such sweep out relative to the endpoints. So this we call the pi 1. This is the class of non-trivial one-parameter sweep outs. So we can do minimax over that guy. Almgren proved that this number is always positive. And here's an example. If you do that for S3, so if you want to apply this one-parameter minimax to S3, the number that you get is 4 pi. So it has to be 4 pi because there's no minimal surface in S3 with area less than 4 pi. It's easy to prove. And on the other hand, there is one family, which is just the family of round spheres, which happens to be an optimal family for this problem, because the sup of the areas is 4 pi for that guy. In particular, the theory tells us that any optimal family for this one-dimensional minimax process must contain a great sphere. In other words, any non-trivial sweep out of S3 by closed surfaces such that the sup of the areas is 4 pi must eventually pass through a great sphere, okay, which are the only minimal surfaces of area 4 pi in S3. Okay, let me very briefly say how the family, this canonical family, is constructed. So the idea is that one has to look at the center dilations of S3. This is a very special class of conformal transformations. So one way to look at this is the following. So you pick an axis in S3. So if you do stereographic projection with respect to this axis, then the center dilations are just those conformal transformations that in stereographic coordinates correspond to dilations with fixing the origin. Of course, you can vary the axis. You can also vary the strength of your dilation. And turns out that this space of center dilations is parametrized by a vector v in the unit ball. So we have an explicit expression here. So those guys, if you look at your axis, you have a north and a south pole. So this transformation is fixed, both the north and the south poles. And as the parameter goes to the north pole, this transformation sends everything else onto the south pole itself. That's roughly the geometry of this conformal transformations. So the idea is that now we start from a surface in S3, we apply the center dilations, so we get this four-dimensional family of surfaces. The Willmore energy is the same because the Willmore energy is conformally invariant, but then we are missing an extra parameter because I said that the family has to be five-dimensional. And the extra parameter comes by considering the equidistant surfaces. So the idea is that first you apply center dilation and then you consider the equidistant surfaces to that guy. So here dv is the function to your conformal image, make the boundary of the sublet. Okay, so again v is in the unit ball and goes from minus pi to pi because we are in S3, so we look at these equidistant surfaces, we know that there's nothing in distance pi or minus pi, so we are sure that we got everything. So that's the canonical family. And again, we can prove that the area of each such guy is bounded by the Willmore energy of sigma. There is a small issue that I might not discuss here, but we actually have to extend this family to the boundary of the parameter space. We need a family in the solid, in the closure of that guy in order to run the minimax process. And in order to do that, we need to do some reparametrization. Because we might, if you want to have some idea of what's going on here, you imagine that you have a surface in S3. So if you start dilating the surface with respect to a point that is not on the surface, right? So the surface is going to disappear at the antipodal point. But if you start dilating your surface with respect to a point on the surface, then the point stays there. The genus that you have collapses at the antipodal point, but the surface gets stretched out, and in the limit you see a great sphere. So you might see points or great spheres, there's something going on. So it just happens that if you reparametrize your family, one actually sees spheres, round spheres of different centers and different radii, varying continuously. So we can understand exactly what happens at the boundary, and in the limit it's always a sphere. So the parameter space, again, is a solid cylinder, the product of a full ball and with the time interval minus pi to pi. Let me say that in the top and on the bottom of the cylinder, the surface is trivial because there's nothing at distance pi. So if you want the surface is 0 here in the top and in the bottom. But on the lateral boundary, for each vector v in S3, we can look at the vertical line passing through v, the boundary of the cylinder. So if you look at the corresponding surfaces along this line, these surfaces will form a foliation of S3 by round spheres with the same center, Q. Of course, the center depends on V. So the boundary behavior, you see round spheres of different radii in different centers, and the boundary behavior is completely determined by the center map, which we call Q. So the center map is a map from S3 to itself, right? And here is our discovery, which was a really great breakthrough in this program. We discovered that the topological degree of the center map is exactly equal to the genus of the original surface. So that was completely crucial. When we found this formula, this identity, we were very excited because we immediately realized that this is the key to the solution, right? So this is how the genus is going to come into play. So the genus is the degree of the center map. So if you want, the boundary of the cylinder is being mapped onto the space of round spheres. So the point is that if the genus of the original surface is greater than or equal to 1, then this map is homotopically non-trivial. This degree is non-trivial. So that's why we don't care if the surface is a torus or genus 2 or genus 3, because the only thing that matters for the argument is that the genus is greater than or equal to 1. The only thing that matters is that this degree is non-trivial. Okay. All right, so we can reparameterize things so that the family becomes now defined in the 5 cube. One can go from the solid cylinder to the 5 cube, of course. So here's just a summary of these properties. So on the top and on the bottom of the cube, the surface is trivial. In the lateral boundary, we see these round spheres, and we know exactly the center. This is given by this map Q. So we can reparameterize things conveniently so that when you look at this foliation by great spheres, the corresponding equator happens to be located at time 1/2 level, if you want, right? So just a reparameterization. So in the boundary, the lateral boundary, at the time 1/2 level, you see great spheres. And of course, if the genus of the original guy was bigger than or equal to 1, this center map has non-trivial degree. And the areas are bounded by the Willmore energy of sigma. So those are the structural properties of the family. So here's an outline of the proof. This is a very rough outline. There are several technical details that we have to worry about. But let me give an outline. So we start with a surface sigma in S3, genus greater than or equal to 1, for which we want to prove the 2 pi square bound. So associated to the surface, we have the canonical family. So we can consider its homotope class, and then we can do min-max theory to such a class. By doing so, we find a minimal surface, minimax minimal surface, which I denote by sigma hat. Because of the area bound, the area of sigma hat is dominated by the Willmore energy of the original guy. And then we have to prove that the sigma hat cannot be a great sphere. That requires a topological argument that I will maybe briefly explain in a few minutes. So if you can prove that this guy is not a great sphere, then its genus has to be greater than or equal to 1. So Elmgren had proved that the only topological spheres that are minimal in S3 are the great spheres. So the genus must be non-trivial. So in other words, summarizing, if we do this minimax process, and if we start with a surface with non-trivial genus, then we end up with a minimal surface of non-trivial genus also. Okay, and then what we do is the following. Remember that theorem B was a statement about the area of minimal surfaces. So forget about the equators. Those are the minimal surfaces with lowest area 4 pi. So forget about those. Look at all the other minimal surfaces. Then one can pick the one with lowest area among all such minimal surfaces. This uses some standard geometric measure theory. We want to prove that this guy is the cars. So the idea is that if this minimax procedure to this sigma 1, we're going to conclude that the index of 1 is bounded by 5. Why is that? This is because our canonical family was 5-dimensional. So you might imagine that if the index happened to be bigger than 5, you would have an extra direction to deform your family and make the area go down, right? So if you could do that, then you could run the minimax again and find a minimal surface with even lower area. That's a contradiction, right? So the guy with lowest area must have index bounded above by 5. But then by Urbanus' theorem, the surface has to be the Clifford torus, and this proves theorem B. Okay, now this is pretty much the whole thing, because in order to prove the Willmore conjecture, what we do is the following. So we start with a surface sigma. We run this process, right? So the Willmore energy of sigma dominates the area of the minimal surface that you constructed, but this minimal surface has non-trivial genus, so its area must be bigger than the area of sigma 1. We just proved the sigma 1 is the Clifford torus, so you get the 2 pi square. So this proves theorem A and the Willmore conjecture. Okay. there is a topological argument to rule out great spheres. That's, of course, completely crucial. Let me just very quickly go through it. The idea is that we prove that if the genus of the original surface was greater than or equal to 1, then the mean max number cannot be 4 pi. It cannot be lower than 4 pi, of course, because there are no minimal surfaces with lower area, but it has to be strictly bigger. So why is that? The proof is by contradiction. So suppose that the number is equal to 4 pi, and in order to just illustrate the idea, let's assume that we were able to find an optimal family. So that means an optimal family, that means that a family for which the sup of the areas is already the optimal number, 4 pi. So this family is parametrized by the 5 cube. Remember that at the time 1/2 level, we saw these great spheres. So the argument is the following. We have this optimal family. Then if we consider a path connecting the bottom to the top of the cube, each such path, of course, is homotopic to a vertical path on the boundary, right? So if we follow the surfaces along such a path, these surfaces will form a non-trivial sweepout of S3, a one-parameter family of surfaces with the property that the sup of the areas is equal to 4 pi, right? Because that was the assumption on the family, that it cannot be lower. So that means that for any such a path, the sweepout that you see is an optimal sweepout for the one-dimensional minimax in S3. So it must cross a great sphere at some point. So every such path crosses a great sphere, and we use that to produce a whole four-dimensional guy made of great spheres. So the blue curve here is a four-dimensional submanifold such that the surfaces are all great spheres along that guy, and whose boundary is the time 1/2 level. Right? So remember that an oriented great sphere can be identified with its center. Right? So what we did is that we just extended the center map that we had at the boundary to this four-dimensional guy. Right? So this means that if we look at the image of this, so since the time 1/2 level is the boundary of this four-dimensional guy, when you look at the image in homology through the center map, the image of the time 1/2 level is going to be the boundary of something. In other words, it's trivial in homology. But it cannot be because the center map, the time 1/2 level, had non-trivial degree. That's the idea. So we extend the center map to the R, and then we compute the homology. We get a contradiction because the genus was assumed to be greater than or equal to 1. Okay, so that was the topological argument. Of course, the version of the paper is a little bit more involved, but that illustrates the idea. Okay, so let me just, before I finish, let me mention some other applications that we found for this minimax theory. So we were able to solve a problem about links in R3. So consider two linked curves in R3, so two disjoint closed curves in 3 space, disjoint from each other. Of course, a basic invariant is the linking number, which counts how many times a curve goes into the other. Here in this picture, the linking number is equal to 1. And it turns out that there is an energy called the Möbius cross energy of a link, given by this very simple expression, which turns out to be again conformally invariant. So that was discovered by Michael Friedman, and Hay and Wang. So again, we have this energy. So the question is, what is the best non-trivial link in R3? In the sense, what is the minimizer? What is the minimizer for among all non-trivial links for the Möbius energy? So the conjecture in 1994 was that if the link number is plus or minus 1, then the energy should be bounded below by 2 pi squared. So if you prove this for link number equal to 1, then you prove this for every non-trivial link. So that was the conjecture, and again, the 2 pi squared number comes up. So in a joint work with Ian Agel and Andre Neves, we have been able to prove that this conjecture is true, and we also prove rigidity. So if the energy of a link, again, we can think of links in S3 instead because of the conformal invariance. So if we look at if we have a link with energy equal to 2 pi squared in S3, then this link must be conformal to the so-called standard Hopf link. It's a very simple link in S3, right? If you ask the question, what is the best realization of such a link in R3, what is the most symmetric one, then the answer is that you have to do stereographic projection with respect to a point sitting on one of the curves, because that curve then will become a straight line in R3, and the other will become just a circle in the plane orthogonal to that line and centered at a point on the line. So this is the most symmetric picture that such a link has in R3. All right, the idea is that there's a different family, right, constructed by different methods, but it has the same structural properties. It's a 5-dimensional family. The center map, actually, the degree of the center map is going to be equal to the Lincoln number, so that's why it's non-trivial. And the sup of the areas is bounded by the Möbius energy. So the previous theory tells us that there must be one surface there with area at least 2 pi squared. That's very roughly the idea here. Let me skip this slide. And let me finish with some recent results that we are very excited about. I'll just mention those very briefly. Okay, so a foundational question of Poincaré asks about the existence of closed geodesics on surfaces. So as far as I know, Poincaré was the first one to consider such a question. Given a closed surface, can one find a closed geodesic, a non-trivial closed geodesic? So this is more interesting on S2 because minimizing methods do not work. If your surface is a torus, for example, you have non-trivial fundamental groups. So you can pick a non-trivial curve, you can minimize length over this class, and you produce a closed geodesic. But if your manifold is the two-sphere, then there's nothing to minimize. So one has to use minimax methods. So that was done by Birkhoff, who proved that this is always the case. So every metric on S2 contains at least one closed geodesic. We can use minimax to prove this. And this inspired a whole class of results. So for example, Lusternik and Schneermann developed a very beautiful theory. One theorem they proved is this existence of 3 simple closed geodesics in S2. There are always at least 3 of those. And in the 90s, independently, combining the results of Franks and Bangert, we actually know that there's always infinitely many distinct closed geodesics. And Hingston also did some important work about how these guys grow with the length. So there's always infinitely many distinct closed geodesics. So our most recent result is the following. Again, this is joint with Nevis. So the theorem is that if you have a compact Riemannian manifold with positive Ricci curvature, dimension less than or equal to 7, this is because some well-known issues about singularities of minimal surfaces in higher dimensions. So if you have a manifold with positive Ricci curvature in those dimensions, then we prove that there exist infinitely many distinct embedded minimal hypersurfaces in M. So that's the theorem. So this settles a conjecture of Yau in the case of positive curvature. So I guess this is the first result of that type. So before I finish, let me just mention that in order to prove this result, we use some families that were considered before by people like Gromov and Guth. And those are parameterized by projective spaces. Okay, I'll finish here. Thank you.
Thanks, Fernando, for this wonderful talk. We have some time for questions, so are there any questions?
Yeah. So in the result that you just announced, what is the role of the positivity of Ricci curvature in the argument?
Right, so that's a good question. So actually we are just polishing the paper. The paper should be out soon. So the only property that we need is this kind of Frankel type property that 2 minimal hypersurfaces always intersect each other. So that follows if you have positive Ricci curvature, and that's the condition that we need. So one can formulate that in terms of this condition also if you want.
Any more questions? But now, let's thank our great speaker.